Hello, in this video I'm going to talk about ideal diode. And most of you know already what a diode is. This is a Schottky diode. It flows electricity from one direction only. And this is an off-the-shelf ideal diode. This is rated at 15 amp and 3 to 28 volt. 3 to 28 volt. So why do we want ideal diode? Ideal means more efficient, very low voltage drop across the diode, and also less heat generation. Most of the power supply, DC-DC converter, battery cell chargers, as well as a solar panel have no anti-backflow protection. So when connected to battery, it is necessary to ensure that the power output of the voltage is always higher than the input of the battery voltage. Or simply connect a diode in series with the positive pole of the power supply to the battery voltage so that the backflow will not occur and damage the power supply. Or in other case, even if the power supply is not damaged, it might drain the battery if left connected without a blocking diode. So that's the reason we need an ideal diode. And again, let's take a look at the ideal diode and let's measure the characteristic of the ideal diode. I have a voltmeter and let's connect a diode and see what happens. So this is a diode. This is a multimeter, I'm sorry, it's not just a voltmeter. So we connect the diode from one side. And on the other side, we also connect the diode. Okay, the voltmeter shows that it's 0.139 volt. That means there's electricity flowing from one side to the other. So if I reverse the connection, Okay, now the meter says open loop. That means it's blocking the current flow from the other direction. So let's take a look at the ideal diode. Most of you know that the ideal diode actually functions like a body diode when it's not connected to ground or so. Let's take a look at the ideal diode and connect one side of the ideal diode. Sorry, it's a little cumbersome to do it with one hand. Okay, I connected the ideal diode and it shows 0.5 volt, 0.511 voltage drop across the body diode of the body diode of the MOSFET. These are two MOSFET in parallel. So it's 0.512 volt voltage drop. Now if I were to switch direction and connect the other way, input to output and output to input. Now I switch direction and connect it the other way. It's open loop. So you can see that the ideal diode, when it's not powered up, it also works like a Schottky diode. So let's take a look at the circuit diagram of the off-the-shelf ideal diode. So this is off-the-shelf ideal diode. I got it from Amazon, and it's 15 amp rated. And one of the customer said that he used this ideal diode to charge a 200 amp hour lithium iron phosphate cell with no problem. But he only charged up to 13 amp, I believe. So this is rated at 15 amp, but the customer charged it all the way to about 13 amp. And this is the diagram, and this is the circuit. There is a IC for the ideal diode controller, integrated circuit for the internal design, which is right here, pretty tiny. And there are two capacitors, one for the input and one for the output. I believe they are 1 microfarad, and there are two MOSFET in parallel, and there's a body diode not shown in this diagram. There should be a body diode in there. This particular IC basically monitors the output and the output voltage. When the input voltage is higher than the output voltage by at least 20 millivolt, it will comes on to turn on the gate to turn on the system. When the output and input voltage is the same or less than 20 millivolt, when the input is less than 20 millivolt, higher than the output, then this is off. So this is how it works. When the voltage is higher on the input side, then it comes on. When the input is lower than the voltage on the output side, it will goes off. So that voltage, in this case, let's say the battery voltage would not be able to backfeed into the power supply voltage. So this is the 15 amp ideal diode. But 15 amp is too low for my what I needed to do, and it's difficult to find something higher for charging cells, because most of the ideal diodes are rated at 9 volts to 50 or 90 volts. So the minimum is like 9 volt. The only one that go down to 3 volts, this one is only rated at 15 amp. So I have to modify it to make my own ideal diode. And earlier you have seen another video that I talk about this ideal diode that I modify that could go all the way to 25 amp. And basically it's the same design but changing the MOSFET to something have lower resistance, and added some heat sink. This is a pretty big heat sink in the back of the MOSFET to conduct away the heat generation. And this is the latest design, which is capable of 67 amp or higher. The reason I say 67 amp, that's the maximum current that I could do in my lab setup. If I have a higher amperage charger, I probably could use it for higher amperage. Again, it's the same design, just a different MOSFET. This one is IPB 180 P04, two of them in parallel, and I added 2 resistor, 10 ohm, connected to the gate. Otherwise, pretty much the same. In terms of construction, I removed one of the original MOSFET, and this one I clipped the link so that this MOSFET is just sitting there, it's not connected, and replaced them with a 2 MOSFET, which is very low internal resistance, one on the front, and I connected the other one in the back, so one in the front and one in the back. I use a pretty massive connection to conduct the current, and also a heat sink, a tiny heat sink, because that's all you need. It doesn't heat up that much. Later on you will see in part 2 the testing, and I measure the temperature rise, pretty modest. So this is the latest design, and let's take a look quickly at the characteristics of the different MOSFET. I showed that earlier. I'm sorry. I will show that in a later video, but at least that's a recap. What was the difference between the different MOSFET? So this is the different MOSFET. This is the off-the-shelf one. This is the latest design. The one is 25 amp. It's already put inside this power supply to protect the power supply. And if you take a look, the voltage to turn it on, I measure the different MOSFET. It needs to be 20, 22, 21 millivolt higher for the input side to the output side for the MOSFETs to turn on. And this is the voltage capability of the MOSFET, 40, 30, 40. And this is the most important item, the resistance from drain to source in milliohm. The off-the-shelf one is 12 milliohm. The one that I put in a 25 amp version is 4.2. This particular one is phenomenal. It's only 2.4 milliohm. It's very difficult to find low internal resistance for a PMOS. NMOS is a lot easier, but PMOS is more difficult to get. And the current capacity is pretty high also. The I drain is 180. This is another important characteristic, VGS, which is the gate to source voltage threshold. Most of these are like 4 or 5 volt, but in order for it to work down to a single cell level, they have to be in this 2-ish voltage. So this one is 2.5 volt, and this particular MOSFET is 2 volts minus 2 volt, and this MOSFET is minus 2.2 volt. So let's do some quick testing of the MOSFET or the ideal diode. This is the setup of the ideal diode, and you got the input from the power supply and the output to a 200 amp hour cell, and the negative is connected directly to the power supply. And I want to measure the voltage drop of the ideal diode. So let's turn this to measure voltage. And voltage drop, this is the output. So I go to clip on the positive terminal of the cell, and this is the input. So I clip to the positive terminal of the power supply. Unfortunately, this is not easy to clip on. This is not easy to clip on. So I use this big guy to clip it on. Okay. now is connected. Okay, this port and these ports are in parallel, so this positive is the same as this positive. So let's turn on the power supply. Now quickly we can see that we are actually measuring the battery cell voltage in the reverse direction, minus 3.288 volt. And with the power supply off, with the ideal diode off, it actually measures negative. This is the indication that the ideal diode is working, is blocking. If the ideal diode is not blocking, then the input and output should be 0 volt. So let's turn on the power supply. Oh, I need to plug that in, sorry. Okay, the power supply is plugged in. Turn it on. Let's set the voltage. Okay, the voltage, let's set it to 3.65 volt. So this is 3.65 volt. And set the constant current charging to, let's do 4 amps of constant current charging. Okay, so this is 4 amp constant current charging, and this is the cell voltage. Let's turn it on, start charging. Okay, it's only charged at 1.58 amp because the voltage is not high enough. Let's bump up the voltage. Let's go high. Okay, now it's charging a constant current at 4 amps. And at 4 amps, the voltage drop of the diode is 0.784 volt already. So the voltage drop is pretty high for this off-the-shelf ideal diode. And so let's lower the current. Okay, the current now is only 1 amp constant current charging, and the voltage drop is 206 millivolt across the ideal diode. Now earlier I told you about the body diode. So if I disconnect the ground, which is the same as disconnect from here, we could take a look at the characteristic of the body diode. So this is connected, and I'm going to disconnect it. Okay, now I disconnected the ground. Now the voltage went up to 0.911 volt. 0.911 volt. The ground disconnected. So let me connect it back up and look at the working of the ideal diode. Okay, now it's reconnected. It's 0.206 volt. So it went from 0.9 volt of the body diode back down to 0.2 volt of the ideal diode. So this is the part 1 of the testing, And part 2 of the video will show charging of a battery. Thank you for watching. Bye-bye.